Hi everyone, welcome back. Myself Ayush Tripathi, mentor and problem setter at GeeksforGeeks, and I welcome you all to this post-analysis video of last weekly contest 167. And the problems were very interesting. Every problem uses some really very interesting techniques of problem solving in a DSA, and we'll discuss all the four solutions and all those techniques that are required to solve these four problems. So starting with the first 3D problem, bit maximization, given a non-negative integer x, and you have to return the maximum number that you can obtain by setting at most two unset bits in its binary representation, such that if a bit is set at index I, you are not allowed to set bits at index I minus 1 and I plus 1. And additionally, we are not considering any leading zeros in the binary representation of x. So you don't have to consider the leading zeros because the leading zeros are infinite. So let's see how we can solve this problem. So let's say this is a binary representation of some value of x, and we can only change at most two unset bit, and we have to maximize the value of x. And so we select the bit which has the maximum bit, a very straightforward and intuition. So the weight of this bit is 2 power 0. This is LSB, least significant bit, and then 2 power 1, then 2 power 2, 2 power 3, 2 power 4, and 2 power 5. Cool. And these are the leading zeros, so we don't have to consider these leading zeros. And then 2 power 5, this is the first set bit from right to left, from left to right, and so it is already set. Then this bit is unset, so we change the value of this bit because it has the maximum bit, and we have to maximize the value of x. So I will change this one to this 0 to 1, and I have used one operation, and the maximum we can use two operation. Now the another constraint was there. If you set the bit at any position, then you are not allowed to set the bit at I minus 1 and I plus 1. So we cannot set this bit, we cannot apply the operation at bit 3, and so the next bit, which is already 1, and then this bit at position 1, it is 0. So I will change this 0 to 1. Now I have performed all the two operation. Cool. And this is the binary representation of the maximum value of x. So yeah, this is the complete solution. We only set the bit which has the maximum bit to maximize the value of x. So here is the implementation. This get method that we have to complete. So count is equal to 2, the number of operations that we can perform. Then I is equal to 30, because here the value of x can only be up to 10 power 9 and 2 power 30, and 2 power 30 is greater than 10 power 9. Then here I am simply skipping the leading zeros, and then iterate over all the bits from higher values of I to the smaller values of I, and while I is greater than or equal to 0, and the value of count is greater than 0. Cool. And then I minus minus, and if the bit is unset at position I, so we mark them as set, that is x or 1 left shift I, and then decrement the value of count. And since we are not allowed to set the bit at position I minus 1, so that's why I have decremented the value of I. And finally I will return this I. And the time complexity is constant, which is O of 32, O of 30 overall. Cool. So successfully submitted. So this is the second problem, maximizing productivity. You are the manager of a factory that produces widgets, and your goal is to maximize the overall productivity of your team by strategically dividing them into two shifts. Each worker has a specific productivity score, and you need to split them into two non-empty groups such that the product of the sum of productivity scores of these two groups is as high as possible. So for this sample test case, the expected output is 100. So the number of workers, which is n, 5, and their productivity is given in the form of array. So an array of 5 elements. And the best way to divide the workers into two groups, the first group with the workers which has productivity 1 and productivity 9. So their sum it is equal to 10, 1 plus 9, which is equal to 10. And the remaining workers to group 2. So 5 plus 2 plus 3. So their sum it is equal to 10. And the product of these sum, that is 10 multiplied by 10, which is equal to 100. And this is the maximum product that we can have. So let's see how we can solve this problem. So the first step is to find the total sum, that is total productivity of all the workers. So that is sum of all the elements of the array. So total sum, which is equal to sum of all the indices from 0 to n minus 1 and a of I. And for this case, for this example, So 2 plus 3, 5, 5 plus 1, 6, and 6 plus 4, which is 10, and 10 plus 1, which is equal to 11. So sum is equal to 11. And this sum is constant. This is very important thing. The sum of all the elements of the array is constant, and every element, every worker must be either in group 1 or group 2. And so let's see what are the possibilities we can have. So the total sum is 11. So let me write all the numbers. So all the natural numbers from 1 to 11. 4, 5, 6, 7, 8, 9, 10, and 11. So what are the possibilities we can have? So let's say group 1 having element with the sum 1. Then another group, that is group 2, is having sum 10, because 11 minus 1, which is equal to 10. So their product, which is equal to 10. Then another, let's say the another possibility, group 1 is having sum 2, and the remaining workers will be in group 2, and then their remaining sum, which is 11 minus 2, it is equal to 9. So their product, it is equal to 18. So at this point of time, I am not checking whether it is possible to select some subset with the sum 1 or not. I am not checking whether it is possible to select some subset with the sum 2 or not. So I am just writing all the possibilities, and then 3 into 8, which is equal to 24, and group 1 has sum 3, and group 2 has sum 8. Then 4 into 7, so 7 plus 4, which is equal to 11, and this sum of this entire array, and their product is, it is equal to 28, and then 5 into 6, which is equal to 30. Cool. And what are the remaining possibilities we can have? So group 1 has sum 6, and group 2 has some remaining sum, which is 11 minus 6, which is equal to 5. So their product, it is equal to 30, and then group 1 can have sum 7 and multiplied by the remaining sum, which is 4. 7 minus 4, 11 minus 7, which is equal to 4. Cool. And then their product, it is equal to 28. And up till group A, group 1 has some, let's say 10, and the group 2 then have some as 1. 11 minus 10, which is equal to 1. Cool. So their product, it is equal to 10. So all these values are repeating. So the thing is, you don't have to check for these values. Just only consider the values up to total sum divided by only the first half values. So starting from index 1, and cannot start from index 0, because the groups must be non-empty, and then it is equal to total sum and divided by 2. We don't have to check for these values, because a multiplied by b is equal to b multiplied by a. So up to total sum divided by 2, and for each element, for each value, I will check whether it is possible to select some subset, such that their sum, it is equal to 3. And if it is possible, then remaining sum is also possible, the remaining sum, which is equal to 8. So just simply check their product and update your answer accordingly. So for every value from 1 to total sum divided by 2, I will check whether it is possible to make this sum or not, and if it is, then I will simply update the answer accordingly. Cool. And this is very standard problem of a dynamic programming, that is a subset sum, whether it is possible to make some whether it is possible to make some particular sum by selecting some subset or not. So let's just quickly define a state. So dp of x comma y, so it is simply a boolean value, true or false, that is whether some y is possible from the subarray starting from index 0 to index I. You can also say from n to I, but accordingly change the transitions. And what would be the transitions? So the value of dp of x comma y, it is simply equal to dp of x minus okay, here instead of saying I, it must be equal to x. So here instead of saying I and j, I have written x and y. Cool. So for every index x, I have two options, that is I will include the value at index x in this subset to make the required sum, or I will simply exclude the value. So we'll explore both the possibilities, that is from 0 to x minus 1, the subarray from 0 to x minus 1. If it is possible to make some y, then it is also possible to make some y from the subarray 0 to x. So do not select this element. Do not select the element at index x. Or dp of x minus 1 and y minus a of x. Cool. So whether it is possible from the previous subarray 0 to x minus 1, whether it is possible to make a sum whether it is possible to make a sum y minus a of x. If this is possible, then I will simply add the element. I'll add the element at index x. So if it is possible to make this sum from the previous subarray by selecting some subset, then in that subset I will simply add the value of a of x, then it would be equal to y. So it is possible to make some y from the subarray 0 to x. So this is basically an exclusion part where we do not include the element, and this is the inclusion part where I will include the element at index x. Cool. And this is a tabulation approach, that is a bottom up DP, and one optimization that we can do. But before that, let me write a pseudocode here. So for all the values of y starting from index 1, and it is equal to starting from 1 and the total sum divided by 2, and we can take its floor value. Then over all the indices I, over all the indices of I, or you can say x, it's totally up to you. So here this x is index, here this x is index, and this y is a target sum. Cool. So I iterate over all the index from 0 to n minus 1, and simply write this transition. Just simply write this transitions. Cool. And in my implementation, I have done one optimization. If you have observed here, and to update the value of this cell dp of x comma y, I just only need to know the previous row values. So what I'm trying to say, okay, let me just quickly remove this thing. So let's say this is a dp table. Let's say this is a dp table with some number of rows, with some rows and some number of columns. So if this is your dp table, then it is not we can further optimize it in terms of space. Let's say this is a row x, row x, row x, and column y. So this is row x and column y, and we want to fill the value of this cell. We want to fill the value of this cell. So every time I am just accessing the above row, the row x minus 1, the row x minus 1, and then yeah, here also I am just only accessing the row x minus 1. So if you are creating a dp table of size, dp table of size n, number of indices, and multiplied by total sum, and divided by 2. So then this is inefficient. You just only have to create an dp table, 1D dp table. Instead of creating this 2D dp table, just only create a 1D array which is of size the number of columns, and keep on updating this. Here, to update the value of dp of x comma y, I just only need to know the previous row. I don't require the values at this row, the values at this row, the values at this row. These two rows are useless for me, are not in use. So accordingly, update the values, and before moving to the next row, just simply update the values at just simply only store the value of this row. Before updating the values of the upcoming rows, store the values for this row, and all the rows which are above this are useless. So this one, and this one. So yeah, this is an optimization that we can do. So now let me just show you the implementation. So this is a method that we have to complete, and first I am finding the sum, total sum, and then half sum, that is a total sum divided by 2, and here I am simply creating a 1D vector of size half sum plus 1 and initializing this with a 0, and it is possible to make a 0. So this is a base case, and then I iterate over all the values, so basically all the indices, and here I am using a for each loop. So yeah, I iterate over all the productivity of this productivity array, and then all the possible values of j, and here the value of j starts from half sum, and it goes till while the value of j is greater than or equal to product. Cool. And j minus. So what I'm trying to say, yeah, this value might be negative, so we have to check a condition. So that condition I have checked here in this for each loop. Then simply dp of j, it is equal to dp of j and or of dp of j minus product. So this is an exclusion part, and this is an inclusion part where we include the current element, and then after this, initialize the answer with 0, and iterate over all the integers from 1 to half sum, that is total sum divided by 2, and if it is possible to select some subset which has some I, then simply update the answer. So answer is equal to maximum of answer that we have so far, and the sum of elements of group 1 multiplied by the sum of elements of group 2. So if it is possible to select some subset which has some I, then the remaining element would definitely have some minus I, total sum minus I. And finally, I am returning this answer. So let me just show you the complete. Let me just try to submit this. And the time complexity is okay. The time complexity here in this case, number of indices multiplied by total sum divided by 2. Cool. And the space complexity here is a linear. And this is a feasible solution because here the number of elements can be up to 100 only, and then the total sum, which is up to 100, it is also up to 100. So overall, it is the overall time complexity. It is n number of indices and multiplied by half sum, that is a total sum, and in the worst case the total sum is 10 power 4, where all the 100 indices are having maximum value, which is 100. So 10 power 4 multiplied by 10 power 4 divided by 2 and multiplied by this 100. So let me write it over here. So the time complexity in the worst case, it is equal to maximum number of indices that we can have, 100, and multiplied by 10 power 4, assuming that all the indices are having the maximum value, which is 100. So 100 multiplied by 100, which is 10 power 4, and half sum. So it is equal to 10 power 4 divided by 4. And yeah, this is the complete time complexity, and the space complexity is linear since we have used this dp vector. So this is the third problem of the contest, counting game. So you are given an integer array ARR of size n, and you have to count the number of good subarrays. And a subarray is good if for every pair of indices I1 and I2, the sum of elements at these indices I1 and I2 is within the range from A to B, where A and B both are inclusive. And it is also mentioned that A is always lesser than B, and a subarray of a single element is always considered as good, and you have to count the number of good subarrays. So let's see how we can solve this problem. And the constraint, the value of n can be up to 10 to the power 5, 3 into 10 to the power 5. So definitely you cannot write a brute force solution. The brute force solution is to iterate over all the subarray, and if the length of the array is n, then the number of subarrays is order of n square, and for every subarray iterate over all the possible pairs and check whether the sum is in the range from A to B or not. And if it is not, then the subarray is invalid. Otherwise, check for the remaining pairs and how much time it will take. So n square subarray, and for every subarray all the possible pairs, so another n square. So the overall time complexity of a brute force solution is n to the power 4, and definitely it is not feasible, and it would not pass all the test cases. So we have to do something better. So this technique is not just only limited to this problem. Whenever you get such type of problem where you have to count the number of subarray or the number of substring, then at least think once about this technique, which is a contribution technique. So a very standard technique, and the contribution technique says instead of finding the complete answer, instead of iterating over all the subarray, find the contribution of each index or the contribution of each element. For every index I from 0 to n minus 1, find the number of subarray starting from index I and is good. So for every index I, count the number of good subarrays. Number of good subarrays is starting from index I. And once you get these values for all the values of I, then you can add them together, and this will be your overall answer. Overall answer is the contribution of each index. Cool. So let's see how we can find the contribution of each index I from 0 to n minus 1. So let's say you have an array 1, then 4, 3 and 2, and let's say the value of A, it is equal to 2, and the value of B, it is equal to 7. So this subarray, all the pairs in this subarray having the sum in the range from 2 to 7. And let's say we try to extend this subarray. So let's say there is another element which is 3. So can I expand this subarray? Can I add this element 3 in the previous subarray? The answer is no. And how we can check this thing? So you can iterate over all the possible values, all the elements of the previous subarray, and find their sum. That is 1 plus 3, 4, which is in this range. Then 4 plus 3, which is in this range. And then 3 plus 3, which is a 6, again in this range. Then 3 plus 2, which is 5, again in this range, 2 to 7. So yes, we can expand the previous subarray, and we can add this element in the previous subarray. But in case if you are iterating over all the elements of the previous subarray to check whether we can expand or not. So this is a kind of inefficient method. And what if I somehow get the sorted array? So let's say the new element that we want to add is 3, and using the brute force method, I have to check for all the elements of the previous subarray. But what if I have this array as in a sorted form? So that is 1, 2, 3, and 4. Cool. So this, I know if it is sorted, then this is the minimum element. So this is the minimum element, and this is the maximum element. Cool. So I just only have to check, that is 3 plus minimum element. 3 plus minimum element, it must be greater than or equal to a, because sum of all the pairs must be in the range from a to b, and this maximum plus 3. So 3 plus maximum must be less than or equal to b. Then I can say we can expand the previous subarray, and we can add this element 3 in the previous subarray. So this is the idea. So the idea here is to somehow get the sorted array, sorted subarray, and we just only have to check the smallest element and the largest element of this sorted array. The smallest element is the first element, and the largest element is the last element of this sorted subarray. So let me write some example here. So let's say the value of a as 2, and the value of b as 7, and the value of n, let's say it is equal to 7, and the given array a, instead of saying this as an arr, I am saying this a only, and the elements are 4, 2, then 4, and let's say 1, 6, and 3. Let's say only 6 element instead of 7 element. So what is the expected output in this case? So I will find the contribution of each index from 0 to index 5, 0 to n minus 1. Cool. So starting, I can use two variables. So variable I and variable j, and the current subarray is starting from index I to j minus 1. So this is an exclusive, and cool. So let's just not focus on this thing where the variable I and where the variable j, that is what is the length of current subarray. And okay, let's just only try to add the element at index j, and we first have to check whether we can add the element at index j in the previous subarray or not. So the previous subarray was valid, and if you add element 4, then again it is valid, because all the subarray of length 1 is good. It is already mentioned in the problem statement. Then the next element, that is increment the value of j. Increment the value of j. So j is now at index 1, that is element 2. Can I add this element 2 here? So can I add this element 2? And yes, the given array is already sorted. Subarray. So I just only have to check whether 4 plus 2, the minimum element of the subarray, is greater than or equal to a, and this 4 plus 2, the maximum element of the subarray, which is 4 itself, and plus 2, it must be less than or equal to b. And both the conditions are true. A is equal to 2 here. Here the value of a is 2, and the value of b, it is equal to 7. So both the conditions are true. So we can add this element 2 in the previous subarray. So yeah, we can add this element. So 4 comma 2, and the next element, and what will be my answer? Okay, we'll come to this part, contribution of current index I very soon. So then we again try to expand it. Can I expand it? That is, can I add this element 4, index 2? Can I add this element? And the answer is no. And if you check for all the elements and compare it and find their sum and compare it with the values a and b, then it is inefficient. So if I somehow get this array as a sorted, then I can simply say first element is the minimum one and the last element is the largest one. So if I somehow get this subarray in a sorted form, that is a 2 comma 4, then I can I just only have to check. Whether there's a 2 plus 4 minimum element, it must be less than or greater than or equal to a, and the maximum element, which is 4 plus 4. 4 plus 4 must be less than or equal to b, and the value of b is equal to 7. So this condition is false. This condition is false. So we cannot expand the previous subarray. And once you cannot expand the previous subarray, then find the answer. So we cannot expand the previous subarray. So simply find the answer. And that is contribution of index I. And what is the contribution of index I? So how many subarrays which are good? So a subarray of 1 element and the subarray of 2 element. So increment your answer by j minus I. Cool. So let me just clear this thing and write a complete steps here. So the first step, if valid, if adding the jth element in the previous subarray, if the subarray is still valid, then expand the subarray. So while subarray is valid, while subarray is valid, simply add a of j. Cool. And once you get that subarray is not valid, then immediately stop and find the answer and increment your answer by j minus I. Cool. And after this, we know the subarray is not valid because we have expanded as much as possible. Now we cannot add the jth element. We cannot add this 4 in the previous subarray. Otherwise, the subarray becomes invalid. Then what is the next thing that we can do? The next thing is to contraction part. This is basically a sliding window problem. So contract, that is a remove, or let me write a contract subarray. Cool. That is remove a of I. And here the value of index I, that is 4. So remove this 4 from the subarray. Remove this 4. And now we are left with 2. In the next iteration, again I will check, can I add this 2 in the subarray? And yes, definitely we can add this 2. So increment the value of I, remove index I, and increment the value of I. Take me to the next index of the subarray. Cool. And in this subarray, I can add this 4. So just simply add this 4. So in this subarray, I can add element 4. So I will simply add 4 here. So 2 comma 4, and the subarray is still valid. The subarray is still valid. So again, we increment the value of j. So increment the value of j, increment the value of j, and can I add this element 1? Can I add this element 1 in the subarray? And yes, we can add this element 1. And to check this thing, I somehow need to know this subarray as a sorted. So 2 comma 4, which is already sorted. And yes, we can expand it. So 1. So it is a 2, 4, and 1. Cool. Then the next index, which is value 6 here. Can I add the 6 in this subarray? No, we cannot add this 6. Otherwise, 4 plus 6, which is out of range from A to B. So this makes the subarray invalid. So this is the second step, that is find the answer. So answer is equal to j minus I. So this is the first subarray contribution of index I. Subarray of length 1, then subarray of length 2, and the subarray of length 3. You cannot say this subarray because it is not good, it is not valid. And how we can check whether we cannot add element 6? So to check this thing, I must have to know that this as a sorted form. So sorted, that is 1, 2, and 4. So that I just only have to check whether sum of minimum element plus a of j, sum of minimum element plus of a of j, if it is greater than or equal to a, then it is fine. It is an happy case. And the last element, which is the maximum element, if the sum of maximum element and a of j, so 4 plus 6, if it is less than or equal to b, which is not true, so that's why we cannot expand the array. And using a brute force method, you have to iterate over all the elements of the previous subarray, and then you have to check for all the possible pairs. So this is an inefficient method. So if I somehow manage this subarray in a sorted manner, then I can easily access the smallest element and easily access the largest element. And the interesting thing, how we manage this subarray, all the subarray from I to j in a sorted form. So for this thing, you can use a multi-map. So this is a problem based on 2 pointers and the concept of hashing. So to maintain this thing in a to maintain this thing in a shorter order, you can use multi-set, not multi-map. So multi-set. So set to store all the elements in a sorted order, and multi because we can have more than one occurrence of the same element. That's why it is a multi-set. And beginning element of the multi-set is the smallest element, and the last element of the multi-set is the largest element. So this you have to just only compare with these two elements and increment the value of j if the subarray is valid. Otherwise, find the answer and contract, that is remove the element at index I and increment the value of I. So yeah, this is the complete solution. Let me just show you the implementation. So here I have declared a multi-set st, then integer I and integer j, then initializing answer with 0, and make sure it must be a long data type, otherwise you might get an overflow error. So while I is less than n, and then here I am expanding the previous subarray as much as possible. So if it is already empty, then add the element at index j and increment the value of j. Otherwise, here I am checking whether I am out of bound or not. And if the value of j is less than n, and then I am checking the minimum element of the set plus element at index j, if it is greater than or equal to a, and the maximum element. So st.end is pointing to the next to the last element, iterator to the next to the last element, and minus minus means take me to the last element of the set, and this simply returns you iterator, and then I will dereference that iterator to get the value, and if that value plus ARR of j is less than or equal to b, then we can expand the previous subarray, and simply inserting this element in the multiset and incrementing the value of j. And once I get that we cannot expand the previous subarray, then my answer is simply equal to j minus I, answer plus equal to j minus I, and then the next step is to contract the subarray, and which is remove the element at index I, and make sure to first find the iterator using the find method of set class of standard template library, and this find method will return you iterator to the first occurrence of ARR of I, and pass that iterator to a erase method, and then erase method will remove the element, remove ARR of I from your multiset. And in case if you are not passing the iterator, if you are passing the actual value, then it will remove all the occurrences of ARR of I from the multiset, which is not the requirement, and that take me to the next index, and here I am simply incrementing the answer. So, and what is the time complexity? The time complexity is just n log of n base 2, as here we are using a set, so that's why logarithmic complexity. And value of I, which is always in increasing order from 0 to n minus 1, and the value of j is also from 0 to n minus 1. So n number of iterations for variable I, and j number of iterations for n number of iterations for variable j. So overall it is a 2n, or we can say order of n, and multiplied by log of n base 2 because of this multiset. So let me just try to submit it, and the extra space that we are using is also order of n. Okay, so we did something wrong. Let me check. Okay, so here we have to write a return answer. Okay, so we are getting a wrong answer. Okay, it was my bad. Yeah, now it's fine. So this is the last problem of the contest, network stability. In a large corporate office, there is a intricate computer network, complex computer network, rooted at the main server, node 1. Node 1 is a root node. This computer is represented as a tree structure, that is n number of nodes and n minus 1 number of edges, where each node represents a computer or a server, and each edge represents a direct communication link between two nodes. The IT department frequently receives query regarding the computer's stability and robustness. Each query consists of two computers in the network, and the department need to determine the critical connection point for these two computers. The critical connection point is the highest common server through which communication must pass to travel between the two queried computer. It basically lowest common ancestor of two node. Once the critical point is identified, the department must evaluate the impact of potential failure at this node. Especially, they need to report the size of largest isolated subnet, the size of largest component that would result if the critical connection point, the lowest common ancestor, and all its direct connection were removed from the network. So for this sample input, the expected output for these two queries is 4 and 2. So let's see how we can solve this problem. But before solving the problem, we can discuss the first example. So this is the underlying tree structure. There is a direct connection from 1 to 2, 1 to 3, then 3 to 4, then 3 to 6, and 4 to 5. So the first query, node 2 and 3. So the LCA, which basically means the lowest common ancestor of both the node in the path from root to x and root to y. So for this node 2 and 3, the LCA is 1. So this is the LCA, and if we remove this LCA, we have to tell the size of largest component after removing this LCA node and all its direct connection. So if you remove this node 1 and all its direct edges, then the tree will break down into two components. The first component has size 1 and the second component has size 4. So the maximum size here is 4. So that's why the expected output, the answer for the first query is 4. So 4 is the answer for the first query. Then for the second query, the nodes are 5 and 6. So node 5 and node 6. The LCA is 3, the lowest common ancestor. So this is LCA node. And after getting this LCA node, we have to remove this LCA node and all its direct edges. So after removing this node 3 and all its direct edges, the tree will break down into three components. The first component has size 2 The second component, let's say this is the first component, then the second component has also size 2, the third component has size 1. So the largest possible size is 2. So the answer for the second query, is also 2. So 2 is the answer for the second query. So I hope the problem statement is clear to you. So first I will solve the problem after getting the LCA, and then we'll check how to get this LCA efficiently, because the constraints are very tight. The number of nodes, and the number of queries both can be up to 10 power 5. So we cannot write a linear algorithm to find the LCA. Linear algorithm means, let's say this is the node 5 and this is node 6. So finding the brute force way of finding the LCA, that is take a direct jump to the parent node. From this 5, take a jump to node 4, then from 4 to 3. So every time we are skipping one, we are moving, jumping to one to its direct parent. That is a linear time complexity solution, and that would definitely not work, because in the worst case, to find the LCA, you have to loop through over all the nodes, almost all the nodes. So that would take O of order of n time, where n is the number of node in the tree. So the overall time complexity using brute force is n, and for every query we have q number of queries. So it is n into q, and both n and q can be up to 10 to the power 5. So definitely this is not a feasible solution, and you would get a time limit exceed verdict. So how we can find this LCA efficiently? So there is a technique which is known as LCA using binary lifting, and this is the prerequisite for this problem. LCA using binary lifting, using which you can find the LCA between any two node in just log of n base 2 time, where n is the number of node in the tree. And what is the perfect order to learn this LCA using binary lifting, which is the prerequisite. So before exploring this LCA using binary lifting, I would recommend you guys to first read about the sparse table. What are these sparse tables? And after this sparse table, explore Euler tour of the trees. And after this, then start learning this binary lifting, LCA using binary lifting, LCA using binary lifting. But still, I will give you the brief overview that what is this LCA using binary lifting. So at this point of time, let's say we know the LCA, and once I know the LCA, how we can solve this problem. So if you know the LCA, let's say this node 5 and node 6, so the LCA of 5 comma 6, which is equal to 3, this 3 is a LCA. And once we get this LCA, I have to remove this 3 and all its direct connection, and then we have to find the size of the largest component. So for this thing, what I can do, I can pre-compute or store the number of node in the subtree of each node. So let's say dp of x. So in dp of x, here this dp is an array. Here in dp of x, I will store number of nodes in a subtree of x. Because once I get this thing, so dp of 3, number of node in the subtree of 3, and the current node also included in its subtree, so it is equal to 4. Cool. And then what I will do, I will iterate over all its children and find the maximum number of node in any component, because I have to remove this node 3 and all its direct edges, this one, and this one. Cool. So answer for the query, that is my answer for the query, it is equal to maximum of the size of the largest component. So what are the components that I will get? So if you remove this node 3, then all its child will get separated from each other. All its direct child will get separated. Basically, this is one component, and this is another component, and basically there is an edge from the current node 3 to node 1, the current node to its parent, and we have to remove this edge, this edge as well. So how many components I will get after removing this 3? So the number of component is equal to the number of childs, and if there is a parent node, then there is also a component, because we are removing this connection also. So how I will get the size of these things? So this is nothing but a dp of 4 and comma dp of 6. So it is equal to the maximum of dp value of all its child, and comma this is this component. And what is the size of this component? So how I can get the size of this component? So this is simply equal to dp of current node, that is a dp of 3. Okay, let me change the color here. So it is equal to dp of 3 minus the number of nodes. So it is equal to n minus dp of 3, n minus a dp of 3. So which is in this case dp of 3 is equal to 4. So the size of this component, total number of node, which is equal to, in this case, 6. So n, the value of n, it is equal to 6. So 6 minus dp of 3, it is equal to 4. So 6 minus 4, which is equal to 2. That is size of this component, it is equal to 2. And the answer is maximum of all these values, dp of all its child, and the size of the above component, which is n minus dp of current node. So how we can compute this value? This dp of x. So this is a recursive problem, and we can memorize it using dp, because the nodes which are in the subtree of 4, let's say this node 5, this node 5 is in the subtree of 4. This node 5 is in the subtree of 4, and 4 is in the subtree of 3. So I can also say this thing, that is 5 is also in the subtree of 3. So it basically the property of transitivity. If 5 is in the subtree of 4, 4 is in the subtree of 3, then I can also say 5 is in the subtree of 3. So first of all, the base case, let me just write down this thing separately. So dp of a current node, let's say dp of x, it is equal to 1, because the node itself included in the subtree, and then iterate over all its children, and find the size of dp value for their children. So for all its neighbor, let's say for int neighbor, and then adjacency list. So let's say, yeah, adjacency list of x, then call the function dfs. So call this function dfs. So this function dfs with the required parameters, and yeah, I'm not going to write it here. So dfs of neighbor, and in this dfs of neighbor, after this recursive function, we are assuming that we know the size of its subtree. We know the size of subtree of neighbor. So then simply add its size in a dp of x. So dp of x, which is equal to dp of x, which is equal to dp of x plus dp of neighbor. Cool. So let me just quickly dry run for this example. So starting with the root node, from the main function, I will make a call to the root node. So node 1, and let's say this node 2 is a first child, and so dp of 2, our base case, dp of 2, and here also I will write dp of 1. So dp of 1. Cool. So dp of 2, which is equal to 1, and it does not have any child. So just simply return from here. So after this 2, we simply return to the parent function, which is node 1. And here I will initialize dp of 1, dp of x with 1, and then I will add the value of dp of 2, and dp of 2, which is equal to 1. So plus 1, and then I will make a call for its remaining neighbors, which is a dp of 3. So initialize the value of dp of 3, which is equal to 1, and make a recursive call to its child. So let's say dp of 4. So this dfs 4, and dp of 4, initialize it with a 1, and then make a call for its children. So this 5, and dp of 5, initialize it with 1, and it does not have any child, so return back to the function, parent function. And in this dp of 4, after returning back from the function, I will simply add the value of dp of 5, because there is a direct connection from 4 to 5. So add the value of dp of 5 and dp of 4. So plus 1, because the size of this subtree is 2, 1 plus 1. And then 4 does not have any child, so simply return back to the parent function, which is 3, and 3 has one more child left, so which is 6. So I will make a call dfs of 6, then a dp of 6, which is equal to 1, initialize it with 1, and it does not have any child. The parent node is 3 and does not have any child, so return back to the parent function, and this is true as well. The subtree of 6 has only one node in its subtree. Then return back to the parent function. In dp of 3, I will add the value of dp of 6. So dp of 3, it is equal to 1 plus dp of 4, and dp of 4, which is equal to 2. So 1 plus 2, and plus dp of 6, which is equal to 1. So overall it is equal to 4, and it is true. The size of this subtree, of node 3 is 4. 4 number of nodes are there. And after this 3, now 3 does not have any unvisited child. So simply return back to the parent function, and dp of 1. Here I will add the value of dp of 3. So dp of 3 which is equal to 4. So overall it is equal to 6. And the size of this subtree, size of subtree of node 1 is equal to 6. 6 number of nodes are there. And once you fill this dp values, and also parallelly compute the values of maximum value in the subtree. Also parallelly compute this value. So also I will parallelly compute this value, that is this answer, maximum of all the subtree child, all the child dp values. So for this thing, what I can do, I can use another array. Let's say maximum. So maximum of x, here in this maximum of x, let me write it this way, max. Okay, max of x, here in this max of x, I will store the maximum number of node in subtree of any child or neighbor, any child of x, any child of x. And how we update this maximum value? So with the same manner, maximum of x, it is equal to maximum of x that we have so far, maximum of x that we have so far, and comma maximum of neighbor. Cool. The maximum number of a node in any component after removing this current node x, then the component, the number of component that we will get is the number of its child, and one more component which is from the parent node. So now previously this is not a constant number. In the previous case, in this case it is not a constant number. Here we can have any number of child. In the worst case it is linear. So if we pre-compute this thing, then it is simply equal to maximum of x. And then this is the first value and another value which is this case, and we can compute this, and this is just a constant term, n is constant and the dp of 3 is constant. Now let's see how we get this LCA. How we'll get this LCA efficiently. After getting this LCA, I can just simply answer the query after this pre-computation. And once I get the LCA, I can answer the query in just a constant time by comparing these two values. Maximum of x and n minus dp of current node, dp of x. I can simply replace this one with x. So LCA using binary lifting. So LCA using binary lifting is a technique using which you can find the LCA between any two node lowest common ancestor in just log of n base 2 time. So let me draw some tree here. So let's say there is a node 1, root node, then from 1 to 2, and then 1 to 3, and let's say 4, then let's say 5, and 6. So the very first thing that we do in finding the LCA is in and out time. That is in time of a node, and when we enter to the node, and the out time when we return back to the parent function from this current node. So let's say for in time I will use a red color pen, and for out time let's say a green color, and I will set a timer for each node. When we enter to the node, when we enter to the recursive function, and before returning from the recursive function, I will set the out time for the current node, and we can use a timer. And you can start with anything. So let's say starting with a 0, and once you enter to the DFS function, so here DFS of x I can say, cool. Okay, so let me write it over here. So DFS of x, and once you enter to the recursive function, just simply assign the timer. So in, that is time in for the current node x, it is equal to time, and then change the value of timer. So that is a time plus plus. That is update the value and then increment the value of this variable timer, and then make the recursive call for all its child. So DFS of all its child, or you can say neighbor. It's totally up to you. And before returning back to the parent function, just simply assign the out timer. So out of x, it is equal to same time, and plus plus. Cool, because after this I have to update the value of timer, the new value of timer, which can be the next consecutive number, consecutive number. So timer plus plus. Use the value of a variable and then increment it. It is post increment. So initializing the timer with the 0, that is for the root node, the end time is 0. Then make a call for its child, which is and also increment the value of timer. So after this 0 we have 1. Then make a recursive call for its child. So for 2, make a call for 2 and DFS of 2, and then in time of 2, which is equal to timer, the value of timer is 1. So 1 and then timer plus plus, timer plus plus. Cool. Then make a recursive call for the child of 2, which is equal to 4, which is 4. So make a recursive call for 4 and the value of timer is 2. So n of 4, which is equal to 2. So 2 and then timer plus plus, it is equal to 3 now. And 4 does not have any child, so you start returning back to the parent function. And before returning back to the parent function, assign the out time for every node. So for this node 4, out of 4, which is equal to time. So the value of timer, it is equal to 3. So 3 for this node and increment the value of timer. So from 3, we increment it to 4 and then return back to the parent function. So for this 2, before returning back to the parent function, assign the value for out time. So out of 2, which is equal to timer, and the value of timer is 4, and increment the value of timer, which is equal to 5. And now we are at this node 1 and it has some unvisited child, so which is 3. So make a call for 3 and once I enter to this function, that is a DFS of 3, I will assign in time for this node 3. So in of 3, which is equal to 5. So assign a time 5 to it and then increment the value of timer, which is equal to 6. Then make a recursive call for all its child. So for 5 and let's say this is the first child. So I will make a recursive call DFS of 5 and assign the value for n time for this 5. So n of 5, which is equal to timer, and the value of timer, which is equal to 6. And 5 does not have any child, so start returning back to the parent function and also increment the value of timer. Cool. So then out of 5, which is equal to timer, so it is equal to 7, and increment the value of timer, which is equal to 8. And then return back to the parent function for this 3, which has one unvisited child. So make a recursive call for DFS of 6 and then assign the value, that is n of 6, which is equal to timer, the value of timer is 8, and increment the value of timer, which is equal to 9. And start returning back to the parent function, but before returning back, assign the out timer for every node, out of 6, which is equal to 9, and increment the value of timer, which is equal to 10. Cool. And then return back to the parent function for this 3, out of 3, which is equal to 10, and increment the value of timer, 11. Then return back to the parent function from 3 to 1, and for this one does not have any unvisited child, so assign the out value for this node 1. So out of 1, which is equal to timer, and 11, and then timer plus plus, and then timer plus plus. So after this 11, increment it to 12, and the out value for 1, which is equal to 11. And why we were doing this step? So this is just to check whether some node is LCA of itself or not. So what I'm trying to say, let's say what is the LCA of 2 comma 3? So the LCA of 2 comma 3 is 1, very simple. And what is the LCA of 2 comma 4? So this is the path from 1 to root to x, and this is the path from root to y, root to 1, 1 to 2, 1 to 2, and 1 to 4. So the longest common ancestor is this node 2 itself. And if one node is a ancestor of another node, then we can say that node is itself as LCA. Here node 2 is a LCA of 4. Here node 2 is a LCA of 4, so I can say this node 2 itself is a LCA. This node 2 is an ancestor of 4, so this node 2 itself is a LCA. And similarly, what is the LCA of 1 comma 6? So here in this case, LCA of 1 comma 6, which is equal to 1. So node 1 is an ancestor of 6, so this node 1 itself is a LCA of 6. Cool. And how to check this LCA? How to check whether some node is is an ancestor of another node or not? So let's say there is a node U and there is another node V, and we have to check whether this node U is a ancestor of node V or not. So if you know the in and out time for all the node, then it's very simple. You can simply say, so this U is the ancestor of V if and only if in timer of U is greater than in timer of U, not greater but less than, because first we make a call for U and then we'll make a call for V. So in timer of U must be less than in time of V, in time of V. Cool. And also out time. First we return back to the parent function from node V, and then we return back from the parent function from node U, because first we make a call for node U and then we make a call for node B. So stack property, first in first out. Sorry, the property of the stack is a LIFO, last in first out. So then out time of U must be greater than out time of V, out time of V. Cool. And there is another thing which is let's say what is the LCO of 3, 3. So LCO of 3, 3, LCO of 3, 3. So the node itself is a LCA, and similarly you can say LCO of 4, 4. So this is the path from root to X and the same path from root to Y. LCA of 4, 4. So in that case, the node itself is a LCA. So instead of writing this symbol, I can simply say less than or equal to, and here greater than or equal to. And if that is the case, then I can say if this is the case, then I can say node U is an ancestor of node B, and node U itself is an LCA. Node U is itself is an LCA. So this is an LCA. So this is another part where one of the node, either X or Y, itself become a LCA, but there might be a case when it is not possible. So what I'm trying to say, let's say, okay, let me draw some tree here. So root node 1, then 2, then 3, and let's say 4, 5. Here I'm drawing the simplest one just for an explanation purpose. So 5, let's say 6, and 7. Let me draw few more number of nodes here, and 9, and let's say 10. Cool. So how we can solve this one? So let's say this is the node X, and node Y, and the query is to find the LCO of X comma Y. So a brute force method is to just take a jump of one node, and from the current node take a jump to the parent node, from this 8 to 7, from this 7 to 6, and from this 6 to 4, from this 4 to 2. Then similarly from here 10 to 9, 9 to 7, and then 7 to 5, then 5 to 3, and 3 to 1. And once both the node X and Y has the same parent, then that node will be my LCA. But this is a brute force methods and takes a linear time, so definitely it is not expected, and not efficient as well. So how we can solve this problem? So the idea here is to take a jump of powers of 2. Take a jump of powers of 2, because we can break any integers in powers of 2. We can break any integer in powers of 2. So for this purpose, what I will do, I will declare a array, 2D array. So let's say the name of this array is up, and this is same as my implementation. So up of I comma j, it's totally up to you. So up of I comma j, here I will store the 2 power jth parent, and please try to pay more attention. Up of I comma j, here I will store 2 power jth parent of node I. 2 power jth parent of node I. Cool. And how I will update this value? So it is simply equal to up of ij, which is equal to up of ij, it is it's very simple. It is equal to up of I and j minus 1, and then from here take a jump of 2 power j minus 1. Cool. So from this node 8, let's say here the value of I is equal to 8. So what is the value of up or dp? It's totally up to you. So what is the value of dp of 8 and 0? So that is this simply means 2 power 0th 2 power 0th parent 2 power 0th parent of 2 power 0th, which is equal to 1. So a direct parent of node 8, direct parent of node 8, so which is equal to 7. So up of 8 comma 0, which is equal to 7. So this is the direct parent, so first parent of node 8. So this is the base case. And then how I will compute this value? How I will compute the value of up of, so how I will compute this value, that is up of 8 and 1. So this is simply equal to up of up of 8 and 0, that is the first parent, and then it's the first parent. So first parent of a first parent. So what I'm trying to say, we wanted to know this value, and this is basically the second parent. This is the second parent, and this is equal to 2 power 1. 2 power 1. So up of I comma j, which is equal to 2 power jth parent of I. So if the value of j is equal to 1, so 2 power 1, which is equal to 2. So the second parent of node I, which is node 8. So this 6 is the second parent of node 8. And how we get this value? So I can also write this 2 power 1, or more formally I can say 2 power j can also be written in the sum of 2 power j minus 1 plus 2 power j minus 1. You can also write it this way. So from here, take a jump of one node. So this can be break down into two components, this one and this one. So this is a 2 power 0, and then 2 power 0. From this 8, tell me the first parent of node 7, and the second parent of first parent of node 7, which is 6, and this node 7 is the first parent of node 8. So to get the value of to get the second parent of node 8, to get the second parent of node 8, first find the first parent of node 8, which is 7, and then first parent of the first parent, that is first parent of this node 7. So if it is still not clear to you, then I can explain it with another example. So let's say the next value, which is equal to deep up of what we can say, 8, the value of I, and let's say the value of j, which is equal to 2. So 2 power 2, which is equal to 4. So 2 power 2, which is equal to 4 in this case. So the fourth parent of node I. So the first parent, second parent, third parent, and fourth parent. So the fourth parent of node 8. So it is simply equal to get the second parent, and from that second parent take a jump of second parent. So from here, up of 8 comma 1. So up of 8 1. From here I will take a jump of, I will first find the second parent. So this component, which is a 2 power 2, and this can be broken as the double of 2 power 1. So this is 1, this is 2 power 1, second parent of node 8, so 2 power 1, up of 8 comma 1. And I already know the values because I will solve this problem for the smaller values of j, and from the smaller values to the bigger values, that is from j is equal to 1, and 2 log of n base 2, and you can take its seal value, just to be on the safer side. I'm taking its seal value. We can take its seal value, where n is the number of node in the entire tree, and starting from the smaller values of j to the bigger values of j. So I already know the answer for this case. So 2 power 2, which is equal to 2 power 1. From here, take a jump of 2, take a jump of 2. And once you get this node 6, once you get this node 6, once you get this node 6, then simply take a jump of 2 from here. So up of 6, comma 1. And I already know the values because we make a recursive call DFS from root node to the child, that is from 1 to 2, 2 to 4, and then from 4 to 6, and then from 6 to 7, and from 7 to 8. So before reaching to node 8, I already know all the parents. I already know all the parents of node 7. I already know all the parents of node 6, and so on. So in this way, I will fill this sparse table. And what this is the sparse tables basically. Yeah. And what is the maximum size? What is the size of this sparse table? So the size of this 2D array up, which is equal to number of nodes. So n number of nodes are there, and if there is one base indexing, then you can say n plus 1. This is the maximum size, and then the value of this j. This j is basically 2 power jth parent of node I, and so it is equal to log of n base 2, and you can take a floor value, but the ceil value would also work. It's totally up to you. So this is the size, and yeah, in this way you can find the LCA. So from here, let me just explain it again, how we get the LCA. So LCA of node X and node Y. So from here, take a jump of maximum jump that you can take. Can I take a jump of 8? That is 2 power 3. Can I take a jump of 2 power 3? No, we cannot take a jump because in this case you will reach out of bound. So can I take a jump of 2 power 2? Can I take a jump of 2 power 2? And yes, definitely we can take a jump of 2 power 2. So the fourth parent of node 8, which is here, which is this 2, and once you get this thing, then from here take a jump of take a jump of 1, take a jump of 0. So after this take a jump of 2 power 0. That is a first parent of node 2, which is the LCA of X and Y. And how many maximum number of jumps that we need to take? So it is simply log of n base 2, where n is the number of node in this complete tree. So I guess this is the complete explanation. Now let me just show you the implementation. And if it is still not clear to you, then I would highly recommend you guys to read about the sparse table URL tour and then explore the concept of LCA using binary lifting. So this is the function which is given to you, and here I am first clearing the agency vector because we have multiple test cases. Yeah, here. So here the maximum number of node is 10 power 5, and here I am adding a constant number 5 just to be on the safer side. But the minimum that you can add here is 1, and then here I am having this agency list, and then array in and out. So in time and out time for all the nodes. Then here we have a sparse table, and the size here is 22. 2 power 22 is much greater than 10 power 5. 10 log of 10 power 5 base 2 is somewhere around 16 to 17. So you can also, instead of writing this 22, you can also change it to 18, 17. Cool. So first I am clearing this agency list because we have a multiple test cases, then building this graph and setting the timer with 0, but it's totally up to you. You can start with any integer, and then there's dp of size n plus 1, where dp of I will store the number of nodes in the subtree of I, and then here we have our maximum array, where maximum of I will store the maximum number of nodes in any subtree child. Then calling this function dfs, and calling this function dfs, cool. And then starting from the root node, which is 1, and for the root node itself, it is the parent of a root node is an imaginary parent. So I am saying node itself is a parent of a root node, and passing this timer, then dp and max. Then here we have our dfs function. So first I'm assigning the end time. Then here we have our base case, that is the first parent 2 power 0, which is equal to 1. The first parent of node 1 is its direct parent. Then I iterate over all the 21 values, and up of I comma j, here in this case node of I, which is equal to simply up of I comma j, it is equal to up of up of I j minus 1 and then j minus 1. Exactly the same thing. This one, this formula. I have used the same formula. And then dp of node, because node itself in its subtree. So dp of node, that is number of node in the subtree of node, which initialized with 1, and maximum of node, which I have initialized with 0. And then here I am having the variable sum and auxiliary, which is not required, and iterate over all its child. And if the child is not equal to parent, we don't have to make infinite recursive call. Then call this a DFS function and add the number of node in the subtree of child in the current subtree, and also updating the value of max, and then assigning the out timer. Then here I am having the function to check whether node u is an ancestor of node v or not. So the in time must be less than or equal to in time of v, and out time must be greater than or equal to out time of v. And if that is the case, then this node u is an ancestor of v. So here I am just simply returning true, otherwise false. Then here I am having a function for finding LCA. So if u is a ancestor of v, then return u, or if v is an ancestor of v, then node v itself is an LCA, so return node v. Otherwise, I will take a maximum jump from here. Cool. And when I will take a jump, so I will only take a jump if after taking the jump, the node, if after taking the jump, the node is not an LCA. So what I'm trying to say, from this 8, I will take a jump of 4. So after taking a jump of 4, that is a 2 power 2. After taking a jump of 2 power 2, I will reach out to node 2, this node 2, and this node 10, and this 2 is not an LCA. This 2 is not an LCA of 10. Cool. This 2 is not an ancestor of node 10. So again I have to take a jump. So what I will do, so here then I will simply take a jump, and after this, once I reach out to 2, so from here I can take a jump of 2 power 0, which is equal to 1, 2 power 1, and 2 power 1, which is the first parent of node 2, which is equal to 1, and this node 1 is an ancestor of node 10. So here I will stop. So here you can also write a break statement, but I do not have a break statement, and then I will simply return the first parent. So basically the first parent of node 2, please try to pay more attention. The first parent of node 2 is an ancestor of node 10. So I will break the loop, and then I will return the first parent of node 2, which is LCA of x comma y. And how much time it takes? It just simply log of n base 2, which is 21 iterations, a constant number of iterations. So yeah, this was about our DFS function. Then here I am having answer vector to store the answer for each query. I iterate over all the queries, and these are the two nodes A and B. Then here I am finding the LCA, and then its parent, which is the up of x comma 0, 2 power 0, which is the first parent of this node x, and initializing the answer with 0. So sum, that is the number of node in the subtree of x, it is equal to dp of x, and then I am taking the value answer is equal to maximum of answer comma max of x. Basically this thing where we have, yeah, this part. First I am taking this max of answer is equal to maximum answer that we have so far, and then max of x, and then we have to take maximum of n minus dp of x. So if x is not equal to -1, that is it is not equal to the root node, we have some component f of x, so which is equal to, and the size of that component is n minus dp of x. N minus, you can also replace this one with dp of x, and then I am simply adding this answer in my answer vector. And how much time it will take? Overall time complexity. So this takes linear time. This also takes a linear time, and this DFH function takes a linear time. But here also I am having this for loop. Here also I am having this for loop. So overall it is n multiplied by 21, or you can say n into log of n base 2. Then iterating over each query, So queue number of queries are there, and for every query, I'm finding this the LCA. So the time for the LCA is log of n base 2. So overall, it is a q multiplied by log of n base 2. So yeah, this is the complete solution, and you can also try to submit it by your own. But let me just quickly show it to you. All right, so successfully submitted. So I hope you guys have enjoyed the video, and make sure to comment your feedback so that I can improve myself for the more upcoming session. So thank you so much for watching this video, and have a good day.